All right. Thank you everyone for being here. Welcome to the Spacecraft Seminar Series, first one of the spring 2024 semester. Today we have an extremely special presentation, extremely targeted presentation from Keith Zook, Principal MBSE at Intuitive. I'll let Keith introduce himself, but today we're going to be talking about reliability, availability, and maintainability, and the options for modeling them using parametric diagrams. Extremely important, extremely relevant. So thank you very much, Keith. And please take it away. One more thing. If everyone would hold the questions until the end, we'll have a Q&A session right at the end. So now, Keith, please take it away.
Okay, great. Thanks, Michael. And thank you, Alabama CubeSat Initiative, for the opportunity to be here and speak with you all. I am, anytime I get to speak on MBSE, I love it. I'm passionate about MBSE. You'll see in my bio slide in a bit, I've been doing it a while. And so anytime I have the opportunity to talk about MBSE, I like to jump on it. Today's topic. So that is a very long title, and it's Michael's fault because he suggested that I spell out all the acronyms. And so bridging the gap between MBSE and RAM using parametric diagrams sort of shortens it up a little bit. This is the third time I've given this presentation. The first time I gave it to unexpectedly, kind of last minute, a group of MBSE folks who didn't necessarily know anything about RAM. And then the second time I gave it, more targeted, was to a bunch of RAM folks who didn't really know a whole lot about MBSE. And so I don't know what kind of mix I have here today. I guess we could do the show of hands. Let's do that. How many folks here? I assume you can raise your hand. I'm familiar with Teams. I'm assuming we can do the same thing here in Zoom.
It's under reactions at the bottom.
Okay. How many folks here have a knowledge, a working knowledge of MBSE? At least some exposure. Yes. Okay. There's one, a couple. Okay. And then sort of on the flip side, how many have really dabbled around in RAM, reliability, availability, maintainability in that arena? Okay. Not so many, but that's okay. I think you're going to find that the concepts that I convey here can be applied not only to RAM, but to a lot of different things. And so hopefully you'll find this presentation beneficial in that regard. So let me get to it. Just a little bit more about me. As Michael said, I'm with Intuitive Research and Technology Corporation. We're based in Huntsville, Alabama. I was based in Huntsville, Alabama up until about a week and a half ago. I just moved to Navarre, Florida. And so really working out of our Niceville office now as of about a week and a half ago. And enjoying it so far, except for being surrounded by boxes here in the house still. You can see my certs, double E by degree, systems engineer by trade, well over 30 years or so. Been an MBSE practitioner for a long time, and I don't even think we called it MBSE back then. I think we called it requirements modeling or something like that. I've worked across several different domains. You can see them there: Army aviation, tactical missiles, missile defense, et cetera, et cetera. Right now, I'm supporting PEO Aviation in Huntsville, assistant PEO for engineering and architecture, and developing an enterprise product architecture, and some of the other intuitive-based projects, doing some work down here primarily for Eglin Air Force Base on their test range, modeling several range systems. I like to do a lot of stuff. Being an avid fly fisherman, I'm happy to be near saltwater. So I'm excited about that. There's three primary takeaways here, sort of a bottom line up front. I'm just going to hit them with you here right off the bat, and that is that MBSE, model-based systems engineering, directly supports the systems engineering process. So whether you're old school and you've been doing it forever, or newer to systems engineering, model-based is an approach that really helps you do what you need to do as a systems engineer. Uh, Within an MBSE construct or environment, parametric diagrams, part of the SysML language, we'll get into that in a bit, really provides a robust analysis capability within that MBSE model environment. And then finally, we can actually our RAM activities, reliability, availability, and maintainability, which are really very analysis and I'll say maybe calculation centric. We can really leverage the MBSE's parametric diagram capability to really give us a very integrated model centric approach. And we'll dive into all of this. The artifacts on the right are there as eye candy. If you can't read them, that's okay. You're not supposed to. We're going to be looking at all of this stuff in more detail coming up. So the purpose of today's presentation is to simply describe how RAM analyses can be performed within a system's MBSE environment. The topics there you see, we'll do a brief introduction to MBSE. We'll talk about the example model and the tool that was used, the language, and various diagram types. And then we'll take kind of a methodical approach into this parametric diagram and analysis by talking about model behavior and then requirements and then structure. And then we'll get into a very simple reliability analysis using parametric diagrams. We'll correlate that to requirement verification and talk about other potential application areas. And then you get to torture me with your questions, which I hope won't be too hard. Okay, model-based systems engineering. We get all amped up over the MB part, the model-based part, and very often we don't remember or think about the SE part, which, as I alluded to earlier, is systems engineering. And so some of you may be familiar with the systems engineering process V. There's a bazillion versions of this out there. I picked kind of a simple one here, but it gets the point across. So before MBSE, as good systems engineers, this is what we did. This was our sort of our guidance, our process. We start up here in the upper left with ConOps and operational needs, and go on down through functional analysis, and then developing structure and performing the synthesis, which is allocating that required functionality to structural components, and back up the other side with putting it all together in integration, and then verification and testing. And guess what? In an MBSE environment, we're still doing that same stuff. It's just that now we have really good state-of-the-art PC tools, MBSE tools that help us do these things and help us uh, supplement them and use graphical notations, languages that have syntactical and semantic meaning. And these tools allow us to really graphically perform our function, whether it's a set of operational use cases up here in the upper left, the system functional architecture through system level use cases and functional flow type modeling or diagrams, on over to the physical structure then that this functionality is allocated to, and even test planning and procedures on the upper right. So I don't want you to think of model based as something foreign. It's still the same systems engineering, just the ability to perform it a little bit more, I would say, efficiently and effectively using models. So today's example model was developed using an MBSE tool, Cameo Enterprise Architecture. You may or may not have heard of it, also known as Magic Draw. And I'm also going to make use of the Cameo Simulation Toolkit. That's an additional add-in or plug-in that goes along with Cameo Enterprise architecture. Notation is straight SysML. You may be aware that there are various frameworks out there, UPDM, which includes DODAF, UAF, the Unified Architecture Framework. And all of those frameworks are great. I'm a believer in UAF myself. I love it. But to keep this simple and not get confused with other terminology that these frameworks bring into the picture, I wanted to stay with straight SysML. So that's the language, SysML. It's a foundational language to all of these various other frameworks. Our system of interest is simply System X. It is completely notional. Any resemblance to anything real is purely coincidental and maybe a figment of your imagination, because there is, it should not come close to anything that is out there. But it could be anything. Okay, it's so generic, it could be anything. And here you kind of get an idea. Even a CubeSat. So keep that in mind as we go. Okay, the MBSE language. So we use, as I just stated, SysML, the systems modeling language. SysML gives us 3 diagram categories, 9 diagram types. We'll talk about them in a second. Very defined element types and relationships between these elements. That's the underlying meta model. And so everything on these diagrams has semantic meaning. We're not just drawing PowerPoint shapes or lines. Everything that goes onto a diagram ends up in the meta model as an actual distinct object with attributes and relations, and that's really the backbone of the model. These element types, how they relate to one another, and how we can put them together to form really diagrams that really tell the story that we need to tell from a systems engineering standpoint. Are we stuck with just what SysML gives us? No, we can customize. We can add custom stereotypes. Here's your tip for the day, though. Be very cautious about doing that. I've done that in the past, and I've got the scars from it. Still, it's not. At first, it may seem like a cool thing. If the language doesn't quite meet your need, go ahead and throw in a couple custom stereotypes or maybe a custom relationship. But here's the issue with that: the second somebody else picks up your model, they're not going to understand what you're talking about, and so that's the downside. And I have found that it's so much better to try to stay within the confines of the language, customize if you absolutely have to, but I would not recommend making a habit out of it. Again, other notations and frameworks exist. We talked about a couple of them, UPDM, UAF. SysML is actually foundational to those other frameworks. So SysML diagrams, there are 3 categories. Behavior diagrams. What does the system do? And you can see there's 4 types of behavior diagrams: activity sequence, state machine, and use case. There is a requirement diagram, and this allows us to put requirement elements on a diagram, show their relationship to other elements. We typically work in hundreds, if not thousands, of requirements, and so requirement diagrams aren't particularly useful when you're really manipulating requirements on a large scale. We find that spreadsheets and tables within the model, which could be exported as spreadsheets, probably work a little bit better, but the real value and power and utility comes in when you may have a requirement or two you want to put on a diagram and show how it relates to other entities in your model. And we're going to show you an example of just that coming up in a bit. And then the structure diagrams. So we're not talking about concrete and steel. We're talking about a system's hierarchy, which we would typically convey in a block definition diagram. interfaces, external and internal, which we would convey in an internal block diagram. And then package diagrams really are for organization of the model, to be honest. A special type of internal block diagram is the parametric diagram, and that's where we're going to be at today. That's going to be our focus. But you can all congratulate yourselves if you've not been exposed to MBSE. You just interpreted your first MBSE diagram, your first SysML diagram. This is actually a block definition diagram. And so these arrows here that are open, they mean something. It means that all these SysML diagrams are the super type. And so behavior diagrams are a type of SysML diagram, as is requirement diagram, as is structure diagrams. And then the subtypes of behavior diagrams are activity sequence, et cetera, et cetera. And so this open triangle means something. And so that's how I interpret this diagram. This is not necessarily a decomposition hierarchy per se. It's showing generalizations and subtypes. Okay. I want to talk just very briefly about behavior because what we're going to be doing is more on the requirement and structure side, but just to cover all three diagram categories, here's an example of, say, a set of system use cases where we define what those top level system functions are. And I just call them use case A, B, C, D, and E. We show that there's a relationship to an external entity, an external actor. And then we elaborate that with activity diagrams. Think functional flow. And again, all of these element notations have a meaning. And so, for example, this long black bar is a fork. It means that we're doing both of these control flows in parallel. So this functionality occurs in parallel with this functionality. You see we have decision logic and loop backs and merging. And so we can model out our required threads of behavior for our system of interest. And you can see kind of the threads going on here. So that's just a very, very quick example of how we model system behavior. So let's kind of shift gears now and really start to move towards this parametric analysis and talk about RAM type requirements in a typical system specification. I don't know if anybody here is familiar with MIL Standard 961 or a data item description that's been around forever for a system/segment specification, 81431A. But this is the basic organization of at least the DoD system requirements specification. And you get down into 3.0, the actual requirements. And of course, you've got to have your scope and applicable documents up front. But section 3 is where the requirements really begin. And so, for example, the capability requirements would be based on the behavior modeling that I just talked about. But let's focus on system quality factors. That's typically, and I say typically because the first time I say that's the rule, then it'll be broken and it won't hold true. But typically, we put reliability, availability, and maintainability requirements under system quality factors. And that's what we've done here. We expand this package out. So in our containment tree, in our model, for what reasons unbeknownst to me, we don't call these folders, heaven forbid. We give them a special name. They're packages. So these are packages, even though they look like folders. So we expand the system quality factors package, and we've got 3 sub packages: reliability, availability, maintainability. We expand those out. For example, the reliability package, and we actually see elements. These are actual requirement elements related to reliability, including the one that we're going to really focus on throughout the remainder here, our required system reliability. And we'll get down here in a second, but you can see the other packages for availability and maintainability have requirements there as well. Again, system reliability is what we're going to be focusing on here. And so here are just, if I were to drag this element onto a diagram, this is what I would have displayed. These are the basic 3-4 aspects of a requirement: the name, of course, the requirement ID, a unique identifier. In this case, we're distinguishing between a threshold and an objective requirement. That's really not going to enter into anything that we do here. The actual text of the requirement, the shall statement, very important, right? And so here you have it: the system shall have a reliability of no less than 0.925. And then the verification method, and we'll circle back to this near the very end. But anytime you're developing system requirements, it's very, very beneficial to have the verification folks involved right up front, and to be thinking about what the methods need to be to verify each of these requirements. In this case, we're going to say, because we don't want to operate our system for 100 years to determine how reliable it is, but we are going to use some analysis methods to determine whether or not its reliability meets its required reliability of 0.925. Here's our same requirement element over here. I've just left it there just so you kind of remember that's what we just looked at. But if I, quote, double click this requirement in the model and open up its specification, that's what we're looking at here. And you see a whole bunch of other stuff. The attributes here that I'm pointing to here on the left, we just talked about. Okay, so I'm not going to go over that again. We also see some relations. Okay, so there's a parent requirement for this system requirement, and I've set up a notional capability development document, CDD, with a handful of requirements, and I've established a derived from parent-child requirement relationship. And so I know that this requirement actually is derived from a higher level operational reliability, that is CDD3. I've established back to verification now, I've established a test case that's going to be further elaborated. It's really looks like a use case, but it's a special case of a use case. It's a test case, and this is going to tell me how we're going to perform the verification. These last two trace relations just basically say that this is a requirement for system X, my system of interest. And then the key, one of the real keys of this whole thing, I've captured the required system reliability as a value property. Now, what's a value property? So a value property, as the name suggests, is any, I hate to use the word, but I have to, any property that that your system of interest or one of its components owns. And so if you think about it, and I think I get into this, I'm probably getting a little bit ahead of myself, but we typically capture non-functional constraints with value properties. I can't model reliability as behavior, right? The best I can do is bring in these values and tie them to my system of interest. And so the way you interpret these value properties is that these are values that are owned by the system. And I know I'm getting way ahead of myself, so let me get to the next slide. Let me get down to the bottom right here, the anatomy of a value property, since we started to get into it a little bit. So typically, well, not typically, it's got a name. In this case, we're looking at subsystem 3's reliability. And so that's the name, subsystem 3 reliability. Value properties can have four types, take on four types: real, integer, Boolean, or string. In this case, these are real values, and then the actual value itself, in this case, 0.980. So what's going on here? So here's another block definition diagram, BDD. And this time we're not doing types and subtypes. We're doing an actual directed composition. How do I know that? I know that by looking at the symbol on these arrows, this black diamond that's shaded in, and these arrowheads. And this basically means that if I'm going to have a system X, I've got to have at least one or more subsystem ones. I have to have one subsystem two, and I have to have one or more subsystem threes. Looking at it the other way, these subsystems do not exist or cannot exist outside of the context of being part of system X. So again, the symbols on each end of the line are very important. And I also should say, and as many of you know, there's weeks long SysML training classes. There's weeks long Cameo training classes. And I'm just really trying to give you kind of the gist of it here in under an hour. So just to kind of put it in perspective, I certainly, as much as I would like to, I can't cover everything. So multiplicity, that's what we're talking about here. That allows us to not have to draw subsystem 3 100 times. If there's 100 subsystem 3s within system X, we can simply represent that using multiplicity. Okay, so what's going on over here? So in the containment tree, if I was looking at subsystem 3, I would see that it has some interfaces that are not shown here. And I would see that it has 3 part properties. So that means it's got 3 subordinate parts. And so you can see them here, subsystem 3 components 1, 2, and 3. Again, another directed composition. And likewise for the other subsystems. Down at the bottom, I see that subsystem 3 has a reliability of 0.980. Now, where did these reliabilities come from? I don't care. For the purpose of what we're doing here, I don't care. It could be from, these could be commercial off-the-shelf elements, and they could all have their own spec sheet stating their reliability. And we use that to figure out what subsystem 3's reliability is. Maybe much like how we're going to figure out what system X's reliability is. So these are given numbers for the purpose of this example. Maybe we've done some actual reliability testing. Maybe we've done some shake and bake type tests, some environmental tests, and so we know that subsystem 1 subcomponents have various reliabilities based on these tests and the results. And so we know that subsystem 1 is actually going to have that reliability. So I think that's all I wanted to say here as we move on into it. So what we're really wanting to know, we know what system X's required reliability is. Well, what is its reliability now based on its subsystems? That's where we're headed here. So let's talk a little bit about the calculations that we want to use. So just as I said, we're going to calculate the reliability of system X based on the reliability of its subsystems. And we're going to do both a simple series and parallel system configuration for these calculations. I pulled some documentation from the web, and I'm not a RAM expert, okay? I'm not a reliability expert. So let me say that right up front, but I pulled some documentation and dug into some of these calculations a little bit, and it didn't take long for my head to start hurting. These are very fundamental, simple calculations. Well, why? Well, there's 2 reasons. One, I'm not smart enough to make them any more complex, and 2, really the real reason, I don't want to overshadow with unnecessary complexity the very basic concepts that I'm trying to get across here with using parametric diagrams within an MBSE context. And so forgive me if these calculations are not complex enough for you. You can go and create your own and make them as complex as you want to. So basically, with series, one system goes down, they all go down, right? The whole system goes down, and that's what you got here. So it's a simple product of each of the subsystem reliabilities. And then we're going to do a compare. We're going to do this inequality here and compare system X's reliability to its required reliability. And then we're going to do the same thing for a parallel configuration. If as long as one system is up and running, or one subsystem is up and running, the system continues to work. And so that equation is a little bit different. You see it here, and then we're going to do the same inequality. So, but here's the key. I'm not going to go off to a Excel spreadsheet. I'm not going to pull out my stubby pencil and a sheet of paper or anything else. We're going to do this all within our MBSE environment. We've already seen how we've been modeling the structure, and we've got components here, and we've got information here. And so we're going to use this as our analysis environment to do what we need to do as far as calculating these values. So 4 primary steps to mechanizing a parametric analysis. One is, the first is defining the analysis context. We've largely been doing that. We've been looking at the model elements that are going to comprise the analysis. We've defined our equations and our parameters. And we've also identified our system of interest, subsystems, and their value properties. And so we've largely done the heavy lifting on that part. Then we need to create the actual parametric diagram. This is what actually implements the analysis. It establishes the associations between those parameters in the equations and the value properties that we just looked at. And then we'll execute it using Cameo Simulation Toolkit. That is what actually executes the analysis equations and provides the results. And then we can do a little bit of what if analysis and scenarios. We can actually, right within the simulation toolkit, change some values on the fly and kind of do a what if and see what happens, and maybe very quickly figure out what some of our margins are. If for example, a subsystem's reliability turns out to be significantly less than what we anticipated, and we just found that out, we could just go ahead and pop that new number in and see what the result is. So gives us a very, very flexible analysis environment. Okay, so establishing the analysis context. Again, the heavy lifting's been done because we figured out the equations we want to use. We've identified all the aspects in our model as far as the systems, subsystems, and their value properties. But we're going to go ahead and model this now. It's another block definition diagram. And by now you know how to interpret this. This is a directed composition. And so we're going to set up our system reliability analysis context. And it is going to be comprised of this constraint block, a system reliability constraint block. And this is a special stereotype, a special type of element specifically for parametric diagrams. And the other part of the analysis context is our system of interest itself and those structural elements that we just looked at. So if you look at the contents of this constraint block, this should all start to look pretty familiar. Here's our series calculation, calculated reliability series equals, and here's our product, subsystem 1, 2, and 3. Here's the inequality that we're going to check for. And then here's our parallel calculation along with its inequality. And then farther down, we do need to go ahead and identify the type of all of our parameters. And so here you see they're all real. So we've done that. On the other side, this is just a simple matter of bringing in those same structural elements that we had previously. And of course, we're only going to the subsystem level. That's really all we care about here. And so really the missing link now, and I don't know if it's obvious, but We still have not correlated these parameters to the value properties over here. So the next step is where we're going to do that. So as we create the actual parametric diagram, so diagram type up here, if you can see it, PAR. So now this is a actual parametric diagram. These are now named instances of the constraint block that we just looked at. So this is an instance of that constraint block, and these are instances now of our system of interest and its subsystems. These are our parameters from our equations down along the right-hand side of the constraint block. And you'll notice that the calculated reliability parameters have no connections to anything. That's because that's what we are calculating for. I think I could have attached them to value properties that didn't have any value, but we were going to get the same result. I just chose not to bind them to any value properties. Again, these are our known equation parameters here. And so they are going to take on the values of their associated value properties. Well, how does it know which value property is associated with which parameters? That's from our binding. So we bind equation parameters to the value properties that they correlate to. And so, for example, subsystem 1, the parameter in the equation, now takes on the value that is going to be provided by the value property for subsystem 1. It doesn't show, yeah, it shows the value here, but this is the actual value property element. So we've got all of our equations set up. We've got our parameters sitting here ready to take on values, ready to be calculated. We've associated these parameters with the various value properties in our model. And look here, so we've got a requirement element that we put on this diagram, and we're showing a relationship that it's based on this value property, which is the required system reliability. And I'm also showing, remember I talked about that parent-child relationship that derived from relationship from the higher level operational requirement. And it's not real glamorous. I just made them both the same. But why did I do that? Well, the simple answer is, as I take a sip of water, my mouth is dry. The simple answer is because I can, and because it helps convey, it helps tell the story. So we're in a model-based environment, and so we want to graphically convey information. We want to tell a story, and so how powerful is it to be able to set up this parametric analysis and also show, well, this is why we're doing it, because I have a requirement here that says this, and it's derived from an operational requirement that says this. And so it's merely to tell a bigger story. Okay. So now I think we're ready to execute. So let me kind of orient you here, starting on the left. So here's our system model. This is the containment tree. This is all that metadata that I have been referring to. This is really the diagram palette, allows you to drag certain types of elements out onto the diagram. Here's the parametric diagram that we just looked at right here. And so I'm going to hit the run simulation button up here, and that's going to invoke the Cameo simulation toolkit. And so what pops up here at the bottom are the various execution panels. The first one is just simply the control simulation start and stop type buttons. The second is the console, and that really provides the status, if you will. If I had done something wonky up here, misconnected something, or did something that was that would not allow the simulation to run, I would get a simulation fail down here, and then I would have to go up and figure out what I did wrong. So Again, this provides the status. And then probably the most important panel for what we're doing is the variables panel. And so this is where we see all of the values known and calculated for all of these various variables. And we're going to get into detail this variable panel here in a moment. So we've executed our parametric diagram, and everybody's happy because we see green. And so this particular tool, because I'm checking a inequality, the best way to convey whether it passes or not is just to simply shade these values as green. And so I know that both the parallel and series calculated values exceed the System X required reliability. And I see the actual values here, calculated parallel, series, and then the required. They all go into that inequality. And so everything is green. And again, everybody's happy. So at the bottom here, you see some red. So what am I doing here? So as I mentioned before, I can kind of do some what if analyses. And so I just kind of messed around with the numbers to try to see what I could do to create both the series and parallel calculated reliability not meeting the required system reliability. And so you just have an example of that. Maybe, and I've actually done it this way in some demonstrations, maybe the user came back and now there's a more stringent operational reliability. So maybe that, what was it, 0.925, maybe all of a sudden that goes up to 0.98, let's say. And so in that case, we would probably get failures here. And then I would be able to go into my subsystem values and maybe see where I might be able to get some margin out of some of those reliability values. And maybe I could tweak subsystem 1 by a couple points and just see what it would take to get me to pass the required system reliability. And then I could take that back to the drawing board and see if we could in fact get that improved subsystem 1 reliability. But you get the point. Once these are set up, you can go in there and change them around and do all sorts of what if analyses. I would be, let me start this way. I've not used it. I've not done it. Okay. But I know it exists. I hear tell of it. And I would be remiss if I did not talk about, or at least let you know, that there's an external evaluator capability. Well, what does that mean? Well, so we've been doing simple math functions. So the capability, at least within this tool, is fairly robust. And so we can do a lot of different types of mathematical equations. And I think there's even a Monte Carlo capability built in. But you may have a much more custom or intense analysis that you need to perform that the out of the box or built, I should say, built-in math functions just aren't going to cut it for you. And so you can actually go to an external evaluator platform such as MATLAB, and you see a few here. There are more. You could use your own custom coding, different evaluator languages. I'm obviously using, I've got English checked here, but you can see the other types of yeah, easy for me to say, evaluator languages that are possible. The fundamental premise here is the ability to expose these parameters to the external evaluator platform. So it goes off and does its thing, but the fundamental key remains. The results come back to the model, and it's still tied to the value properties of your system and subsystem. So nothing here changes per se. We just have the ability to go out and do much more custom and I would say maybe more intense external calculations. Okay. And again, don't ask me any questions on this. I've not done it. I would like to one day. So we've talked about requirement verification, and let's talk about it a little bit more here. At the top, I have another example requirement. It's not important what the requirement is, but here we have a verification method of demonstration. Okay, so we're not going to just do an analysis. We're actually going to walk through a procedure that demonstrates that we meet this requirement. I've got a test case set up. It's got a name, which is not important, but I've got an activity diagram that elaborates this test case. This is the process flow that we're going to use to demonstrate that the system meets this requirement. Okay. Now down to our old friend, system reliability, the same requirement we've been dealing with. And we've talked about the fact that it's got a derived relationship from its parent requirement. We've talked about the fact that it's based on a required system reliability value property, and you see it there. But now I'm also going to add its verification test case, system reliability verification, and I'm going to elaborate it with an activity diagram. But this is going to be a very simple activity diagram. It is simply going to say, you know, that parametric analysis that we just did, go do that. And that's how we're going to verify that the system meets its required reliability. So very simple and straightforward, but this should hopefully maybe get you to thinking about how early on, as you're developing requirements, as you're doing your modeling, as you're establishing value properties and everything, you can start thinking about the verification phase, and it doesn't have to come as a big surprise at the end of your project. You can be planning this well in advance from day one and really have your ducks in a row, have everything tied nicely together as you see here. And so just a glimpse of what an integrated approach to requirements verification might look like within this very simple parametric analysis context. Other potential applications. This is just one very simple example. Okay, what about other RAM calculations, availability, mean time between failure? What about other physical aspects of your system? If we're in an aircraft domain, weight roll up is incredibly important. Center of gravity. What about risk calculations? Likelihood times consequence, right? We've all seen that. So basically, so here's the message. Anything that can be represented as a value that is owned by the system or one of its components can be used in a parametric diagram analysis. So really, the sky's the limit. This was just one example focusing in on the domain of RAM and reliability, but you could literally apply this to so many things. And again, I think I mentioned this at the start, or maybe I didn't, maybe I thought I did. The whole area of parametric diagrams and parametric analysis is right there. It's available to anybody doing an MBSE project, any MBSE practitioner. I think the challenge is getting out of our paradigms that say, "Oh, I got to do a calculation. Let me whip out my Excel spreadsheet, or let me go straight to MathCAD or something like that." And we fail to realize, or maybe we don't immediately see, that we could do this all within an integrated fashion, as I've shown you, tied to our system structure, even to behavior. So I will get off my soapbox, and that's it. So if anybody has any easy questions, I would be happy to answer them or attempt to answer them. And I hope you found this beneficial and worthwhile. Thank you.
Thank you very much, Keith. that was exceptional. Done a bit of reliability modeling and some of our other SysML models, but it was really nicely laid out here in the process for making it come to fruition and make it executable. That was really nice. I've got a couple questions, but I'd like to open the floor for the students. If anyone's got anything. Yeah, I know that the hands weren't raised early on, so people weren't exactly familiar with reliability. So if you had any follow-up questions to increase your awareness or anything at all. I'll start while the students brainstorm. So would it, the first step in your process when you're making your use cases, when you're doing the functional decomposition, you started with system reliability, and then later you talked about the mean time between failures and other types of uh, quantifiable measures of RAM. Are you thinking about functional or performance reliability when you're defining the use cases? I mean, how early in the process are you thinking about reliability? Because I do
So
hear some people who work in the business say that they lament that reliability is only considered as an afterthought.
yeah, no, you're spot on. You could and you should. So again, not a reliability expert, but I do know this. We can actually associate value properties to functions, which would convey their performance. We could, and in conjunction with that, we could also probably set up value properties that convey reliability associated with the performance of a function. There's a whole nother realm of reliability and function hazard analyses that I did not get into. There's some folks at Intuitive that do a lot more of that than I've ever even thought about. Um, but they use the behavior model to perform functional hazard analysis. And so it entails looking at basically each function and figuring out, okay, how can it fail? What are the ramifications? And of course, it's not even so much the function failing, it's that component that performs the function, right? And so there's a direct tie-in between components that perform these functions and their reliability, and then how that then affects the functionality or the behavior of the system. And I know I wandered all around there in answering that, but I hope I got close to answering your question, Michael.
You did. While modeling it, we can think about the reliability as early as the use cases, particular to which system elements perform which functions. You
Absolutely.
your in this example that you walked through with System X, this was specific to the requirement type threshold. It was a threshold requirement. I'm not intimately familiar with the different kinds of requirement types that SysML allows here, but what are there other requirement types that are pertinent to RAM modeling other than threshold requirements?
Yeah, so I would not make the correlation that threshold is peculiar to RAM. So in our domain, and again, I'm coming out of the DoD space. I don't know where everybody else lives, but we quite often when we get a source requirement document that we need to start dealing with and flowing that down to system requirements, sometimes there are requirements that are categorized as threshold, meaning uh, that's the bare minimum. That's, if you can do that, you've met the requirement. That's all we need. However, the objective requirement is if you can squeak it out. So the threshold might be 5, and the objective might be 7. And if you can squeak out that 7, um, that would be phenomenal. Or maybe there's a planned product improvement phase where the actual objective is to go from all the threshold values up to the objective values. So it's not a reliability peculiar thing. And quite honestly, I'm not even sure it's a standard Cameo thing. I think that's a custom attribute that we probably added. Okay.
It's helpful. I've got more questions, but I'd like to, open the floor. Students, you got anything? Hopefully
Put
the
everybody
awareness.
put
No, no,
everybody to
no.
sleep, I think.
Not at all.
They're
Um,
speechless. They're overwhelmed.
So you talked about the allocating a value to a function, that representing its performance value. Do you differentiate between function and performance and reliability? I mean, you here are doing the reliability of the subsystem components themselves, but I've seen reliability done as functional reliability as well. It's not just the subsystems or the components, it's the reliability of the specific functions or capabilities owned by that component. Is that something that you've worked with or found success in?
So again, for the purposes of this example, we've just simply modeled reliability as a non-functional constraint. Okay, you're exactly correct. There's all kinds of ways to approach this and ways to deal with reliability. So I personally have not performed functional hazard analyses, which I think is kind of what you're getting at, using value properties correlated to functions, which are then allocated to components which have a particular reliability. I have done a lot of, though, just setting up value properties which convey the performance aspect of a function. And I will just hasten to say that's a very overlooked thing in MBSE. We're very intent on modeling the functional behavior, but I'm always quick to point out every function or action that you define really is an opportunity then to think about its performance. So that action in the activity diagram is simply what the system does. How well, how far, how fast, how high, those are aspects of performance, and every single one of those functions is a candidate for thinking about what performance aspects should be related. And that's where reliability can also fit in. And so you bring it up really valid points, Michael. I've approached reliability from a very static, simple, non-functional constraint perspective. You're coming at it from the functional side, and
You got to start
it's all
somewhere.
good. It's
Yeah.
all good. Yeah.
Okay. Well, Keith, I really appreciate your time. Thank you so much for the insight and the acumen. This has been eye-opening for me, and it was great to see the process laid out so specifically. So thank you very much for your time, and we hope that you have an epiphany of another lecture that you'd like to give at some point. So thank you.
I've got a few more in the bag, so we can talk.
Would love to. Thank you very much, students. Appreciate y'all's time. Y'all have a wonderful night.
Thank you.
Thank you. Out.
Thanks for your time.
Thank you.
Thank you so much.